Okay, in today's lecture and couple of next few lectures, I'll just cover the some of the recent research results that are published in the area of biomaterials, so that you can have a feel at how the material development in the area of biomaterials are driven by certain issues which are related to both physical properties as well as biological properties. So, this is the physical properties as well as the biological properties. So, certain properties as far as the physical properties like strength, toughness is concerned, or biological properties like in vitro cytotoxicity or cell growth, cell proliferation, cell fate processes, as well as the in vivo biocompatibility property, those will drive the development of hydroxyapatite based bioceramic composites. Now, the fundamental understanding or the basics of the physical properties or biological properties of tissues as well as synthetic materials that were already discussed in the last several lectures. So, these are the kind of equipments like which are these are the facilities which are used in this biomaterials research. So, this is called the SPS, that is called spark plasma sintering machine. Essentially, this spark plasma sintering machine involves putting a powder compact here in this graphite die punch assembly, and then you are flowing a high current both through this graphite die wall as well as through this powder compact. Now, this is the anode, this is the cathode, and in high current when it will pass through this powder compact, that will help in the densification or consolidation of the materials. It shows that three particles which are in contact with each other, and then how this current will pass through the particle powder surface, and this is the spots where this heating will take place, because that will the spots, contact spots, that will offer resistance to the current flow, and as a result Joule's heating will take place, and that will lead to the large temperature increase. So, here the temperature will increase to a high value, and that will help in the enhanced mass transport. Now, this is the bacteria culture facility. So, this is this vertical laminar flow where you can do culture of the different bacterial strains like E. coli bacteria or Staphylococcus species and so on. So, this is the cell culture facility which are also used, and this cell culture facility has several equipments which includes the microscopes like phase contrast microscopes or fluorescent microscope, as well as this laminar flow wood where people do this, people use it as a wet bench. We have this CO2 laminar CO2 incubator for incubating the cells. This is the ACM image typically showing that how the cells proliferate in silver doped hydroxyapatite. Now, what was the central theme of this biomaterials research? Central theme is to develop the bone analog or hard tissue replacement material. Bone analog means it is like the materials which will have set of properties which will be just sufficient to mimic the bone properties, or hard tissue replacement, hard tissue in other words a bone. So, that hard tissue replacement is that like for any orthopedic applications, if you want to replace the hard tissues, then the materials which can be used, those materials need to have optimal combination of physical property, that is hardness, strength and toughness, and biocompatibility. Now, there are certain terminology aspect in the material science. The hardness, strength or toughness is called mechanical properties, but in biological literature many times in the many standard textbooks, these material properties like hardness, strength and toughness, they are mentioned as physical property. So, physical property in material science, they are mostly mean the density, thermal conductivity, resistivity, all those are physical property. So, this is just a nomenclature or designation, the way people tend to describe certain properties in the two different community. One is the material science community, one is the biological community. Now, through the next 50 or 60 lecture slides, I will just go through some of the results which are obtained in the hydroxyapatite based systems, which are reinforced with mullite or silver or zinc oxide. So, this addition of these different second phase or either ceramic phase or metallic phase, they serve some purpose. Then third one is the Macquart based dental glass ceramics. These glass ceramics are used for these dental restorative applications. Then I'll show you that how these different properties that you can obtain in these glass ceramic materials. The fourth one is that polymer ceramic biocomposites, that is for trabecular bone generation, and also we have developed another set of polymer ceramic composites for hard tissue replacement applications. Now the biocompatibility, it has been dealt earlier also, but at every lecture certain important concept or certain important definition I feel like reminding you, so that you are absorbed with this important concept or important ideas. So to go back to the very fundamental definition of biocompatibility, which is proposed by David Williams, who is the editor-in-chief of Biomaterials journal. Biocompatibility refers to the ability of biomaterial to perform its desired function with respect to a medical therapy. I again repeat, biocompatibility is such an important concept, it clearly depends on the application point in mind. So application means if it is a bone replacement or orthopedic applications, then you require a set of biocompatibility property. If it is for blood conducting devices like heart valves, you require a set of biocompatibility properties which is different from what you need for the bone replacement applications. Now without eliciting any undesirable local or systemic effects, if you remember what I meant by systemic effect, now systemic effects can be acute, can be subacute, can be chronic, or can be subchronic, depending on how this host response that is observed or realized within certain time frame, right? Now those details I have already discussed in details. In the recipient or beneficiary of the therapy, who is the recipient or beneficiary? That is the human being. But generating the most appropriate beneficial cellular or tissue response. Most appropriate beneficial cellular or tissue response means like that how these cells will behave when they are coming in contact with the biomaterials. That is what is meant by most appropriate beneficial cellular or tissue response. Whether that fibrous capsule will form in vivo when this material is implanted on specific sites. In that specific situation, and optimizing the clinically relevant performance of the therapy. Now whatever was the application point of view in mind, your biomaterial should be able to perform in a clinically relevant manner. So it is like a more basic definition of the concept biocompatibility. Now as I said that that development of that new generation biomaterials, it is driven by certain factors. Now what are those factors? First one is that if you look at this cortical bone, that green row, what you notice that depending on anatomical location, you have the range of properties which includes tensile strength 60 to 160 megapascal, compressive strength 130 to 180 megapascal, fracture toughness 2 to 12 MPa square root meter, and elastic modulus 3 to 80 gigapascal. Now if you compare the cortical bone property with that of the hydroxyapatite, what you notice here, then in case of hydroxyapatite, you have this tensile strength, compressive strength, as well as elastic modulus, which are just matching with them or which are even higher than that of the cortical bone properties. However, if you look at this cortical bone fracture toughness and the fracture toughness of hydroxyapatite, then fracture toughness of the hydroxyapatite even does not touch the lower bound toughness of the cortical bone. So that was the point to be noted here, and why I am putting so much emphasis on the hydroxyapatite, because hydroxyapatite is the major inorganic component of the natural bone. So therefore, if the hydroxyapatite has good biological properties, but you have to also know that hydroxyapatite lacks certain physical properties, and that is the reason why hydroxyapatite cannot be used as a bulk implant materials for several bone replacement applications. Now if you go to the other metallic materials, for example titanium or stainless steel or titanium alloys, again if you see their elastic modulus is higher than around 110 or 120 gigapascal, which is higher than that cortical bone. So if the difference is too high, as I have mentioned in earlier lecture, then it can cause the aseptic loosening, because this materials itself will bear most of the load. If you look at the stainless steel, now stainless steel has an elastic modulus of 200 gigapascal. That shows that stainless steel elastic modulus is more than double that of the cortical bone, even the highest range, highest bound modulus. So that is the reason that stainless steel in many cases, except the stem of the total hip replacement, cannot be used as a bone replacement materials. Now therefore, if I summarize that what are the advantages and disadvantages of hydroxyapatite, hydroxyapatite is a typical, it has a chemical formula of Ca10 PO4(6)OH(2), and that is the main mineral composition of human bone and teeth. So if you have this teeth also has a large amount of the hydroxyapatite, and because it is the major mineral composition of the human bone and teeth, that is the reason it can easily bond biologically with living bones and tissues, and hence hydroxyapatite shows bioactivity. Now what are the disadvantages of the hydroxyapatite? The first one is that it has poor mechanical properties, that is the hardness, strength and toughness variation, and definitely it is unsuitable for load bearing applications. The second one, it is more critical because when you put the material as an implant inside the in vivo condition, other factor that needs to be considered as the prosthetic infection. Prosthetic infection means, like if you put this implant at the specific sites, lot of bacteria they will be attracted, and if they are attracted and if they stay happily on the implant surface, then that cause prosthetic infection. Now in order to avoid the infection, you have to develop some materials which has good antimicrobial property. Unfortunately, hydroxyapatite does not have antimicrobial property. Okay. Now that has been shown in the next slide. Now if you see this particular slide, this ACM image is actually taken after the 4 hours of incubation of E. coli bacteria on the hydroxyapatite surface. Now this E. coli bacteria is the gram negative bacteria, which has a typical aspect ratio of 5:10, that is aspect ratio means length to diameter ratio, and this is a typical rod like bacteria, and they are actually happily surviving on this material surface. So that shows that hydroxyapatite does not have a very good antimicrobial property. Other things that important thing is the hydroxyapatite, that it has very it is highly brittle. Now this is your Vickers indent. Now if you look at this indent and if you look at the region surrounding this indent, then what you notice here, that region just adjacent to the Vickers indent, this is the region where spalling takes place, spalling or chipping of materials that take place, and because these cracks are extensive, that this extensive crack formation leads to spalling. However, this crack length, which is called radial crack length, which actually from all the corners of the Vickers indent, those cracks are also relatively larger in length at the 50 Newton load, which indicates that their fracture toughness is essentially very low, and if you determine this fracture toughness is less than 1 MPa square root meter. So there are two aspects which are important, which drive the development of hydroxyapatite based composites. The first one is the poor fracture toughness of hydroxyapatite. The second one is that lack of bactericidal property. Bactericidal means there is a lack of ability to kill the bacteria in contact with that particular material. Now the question is that what are the solutions? There are two solutions. One is the coating approach. Coating is like, you can coat this hydroxyapatite on the titanium or titanium alloys or stainless steel substrate, whichever it is true. So you can coat the stainless steel substrate or titanium or titanium alloys. So thereby you are trying to combine the good bioactive property of the hydroxyapatite with good strength property of the titanium alloy. So you are essentially combine good mechanical or physical property of the metallic alloys with the good bioactive properties of the ceramic coatings, that is hydroxyapatite. But there are major concerns, major problems is that coating thickness as well as the adhesion of the coatings. Now coating thickness typically means if the coating is not very thick, then the coating does not have a longer lifetime, and if the coating is very thick, then the coating can be ruptured or the coating can be delaminated from the substrate. So both the aspects actually create limited lifetime to these hydroxyapatite coatings. Now the composite approach is that hydroxyapatite composite with optimal amount of a biocompatible phase can be developed to achieve better physical properties without compromising on the biocompatibility and the bactericidal property. Now what this statement means? This statement means that you can add the second phase X or Y in a particular amount, provided that X and Y are not toxic or non biocompatible in nature, and with the ultimate aim to achieve better physical properties. Better physical means better toughness properties or strength properties. However, that increase in the physical properties should not take place at the expense of biocompatibility or the bactericidal property. Okay? So, this is the major thing that is important for this composite or bulk approach. Now, some more information on this hydroxyapatite based composites. Now, in various hydroxyapatite composites, particularly with ceramic reinforcements, now if you see the ceramic reinforcement like alumina, zirconia, glass or glass ceramic or hydroxyapatite whiskers, fracture toughness is reported to be enhanced up to 1.5 to 2 MPa square root meter. Because as you have noticed that in the last to last slide I have mentioned that hydroxyapatite fracture toughness is around less than 1 MPa square root meter. So, what this statement means? This statement means if you add alumina or zirconia or hydroxyapatite whiskers, the fracture toughness can be modestly improved, and this modest improvement is shown in the final toughness values of up to 2 MPa square root meter. Now, what are the critical issues that should be considered in the development of hydroxyapatite? The first one is the phase stability in terms of the dissociation of hydroxyapatite. Now, hydroxyapatite, as you know, that it has a formula that Ca10 PO4 whole 6 and OH whole 2. Now, this can be transformed to Ca3 PO4 whole 2. Now, Ca3 PO4 whole 2 is the called tricalcium phosphate. Now, this tricalcium phosphate is popularly known as TCP. Now, this has two polymorphs, one is alpha TCP and one is the beta TCP. Now, this transformation of hydroxyapatite to alpha TCP or beta TCP, that take place more easily or more favorably in some of the composites where you add this alumina or zirconia as a reinforcement. Other problem is that with this hydroxyapatite, suppose you add zirconia to hydroxyapatite during sintering, if you do not control the sintering conditions fairly well, then what happens, this zirconia can react with, now first of all, this hydroxyapatite can release this TCP or can be dissociated in TCP, and if you balance these reactions, then you will end up having one CaO, 1 mole of CaO from 1 mole of hydroxyapatite. And this CaO can further react with zirconium oxide, and this can form calcium zirconate. Okay? So, what I am saying here, that these sintering reactions also can take place depending on what kind of reinforcement you add to this hydroxyapatite. Okay? And if your sintering reactions take place, then you cannot take full advantage or 100% advantage out of the fact that you have the hydroxyapatite in the material. Third one is that it has a lack of crack growth resistance or damage tolerance property, and this damage tolerance property is mostly the toughness or strength property. The fourth one is the retention of good biocompatibility or bioactivity property. Now, this good biocompatibility or bioactivity property is lost when your hydroxyapatite is transformed to tricalcium phosphate or it undergoes sintering reactions. Fifth point is that significant adherence of bacteria on the hydroxyapatite surface, and that essentially leads to prosthetic infection or infection at the implant site. Now, typically in the laboratory scale synthesis route, hydroxyapatite can be synthesized by what is known as suspension precipitation route. Now, what is suspension precipitation route? You can start with the calcium oxide as a precursor. Another precursor can be orthophosphoric acid. Now, this calcium oxide and orthophosphoric acid, you can allow them to react, and that reaction produces hydroxyapatite. Now, some of the experiments that was carried out to improve the hydroxyapatite toughness, that was to add mullite to hydroxyapatite surface. Now, this is the as synthesized hydroxyapatite surface. Now, if you look at this part, this is 2 micron here. So, therefore, individual particles here, which is largely spherical in nature, these individual particles is certainly in the range of nano size of 100 nanometer or little bit higher or lower than 100 nanometer. The other important thing is that whether you have the phase pure hydroxyapatite or single phase hydroxyapatite that can only be confirmed by the Ca by P ratio. And this Ca by P ratio you can measure by ICP, that is the inductively coupled plasma atomic emission spectroscopy, and from that you can find out the Ca by P ratio. If it is 1.67, then only you can say that this hydroxyapatite is a phase pure hydroxyapatite. Now, if you do this normal sintering, pressureless sintering of hydroxyapatite with the mullite, for example, just to improve the fracture toughness, I will show you why mullite increases the fracture toughness, how mullite content increases the fracture toughness. Now, these sintering experiments were carried out for 2 hours in simple air at different temperature, right from 1000 to 1400 degrees Celsius. It was not known that at what temperature you can obtain sufficiently high density in the hydroxyapatite mullite, and that was the reason that why sintering temperature needed to be optimized. Now, if you look at this around 1300 to 1350 degrees Celsius, you get close to 90 to 95% theoretical density. Now, this is XRD spectra, and this XRD spectra essentially tells you that when you have a starting powder, you have this characteristic hydroxyapatite peak and you have also the mullite peak. Now, when you add this 30 weight percent mullite or 10 weight percent mullite to this material and sinter them at 1350 for 2 hours, what you see here, multiple peaks, like you have this TCP, that is alpha TCP peak, you have the hydroxyapatite peak, you have this star one, that is the beta TCP peak, you have the galenite peak, etc., etc. Now, what is this galenite? Galenite is C2AS. C2AS means 2 calcium oxide, alumina and silica, that is a ternary compound. Now, you are starting with your only hydroxyapatite and mullite. Now, when you are seeing that all these multiple phases are formed, what it means? It means hydroxyapatite must have dissociated to form this alpha and beta TCP, that is number 1, and subsequently there are some other sintering reactions must have taken place to explain the formation of this galenite and other phase. Now, what we have proposed is that if you start with this Ca10PO4-6OH2, that is hydroxyapatite, it forms this trial calcium phosphate TCP, it releases CaO. Now, this CaO can react with this 3 alumina 2 silica, which is nothing but mullite. So, mullite is the solid solution of alumina to silica, and that is 3:2 ratio. Now, if you look at these reactions, then CaO reacts with this mullite and then it will form calcium aluminosilicate, and this calcium aluminosilicate, the formation is also associated with 1 mole of alumina. So, all these sintering reactions essentially explain that why these multiple phases are formed during this sintering. Now, typical ACM image essentially tells you that you have a microporosity in the structure, and this porosity is roughly 5 to 10 micron in size. Okay? And this microporosity is also associated with certain grain boundary phase, and most likely it is this calcium aluminosilicate phase which is formed along this grain. So, this is your tricalcium phosphate or hydroxyapatite CAP grains. Now, more analysis was carried out using the transmission electron microscopy. Now, what you see here, that mullite is the needle like structure, okay, and these mullite particles are dispersed in the microstructure, and there is sintered reaction product, and this sintered reaction product is nothing but C2AS, that is the 2 calcium oxide, alumina and silica, that is calcium aluminosilicate. And what you see here further, this C2AS is formed at the interface of hydroxyapatite, mullite, and you have the another tricalcium phosphate. Now, if you know the microscopy well, then if you take the selected area diffraction pattern from individual hydroxyapatite or mullite or the sintered reaction product, then you can confirm the presence of all these phases. You can index it just like you can index the XRD phases. Similarly, you can index from the selected area diffraction pattern, and that is what has been done here. You can see this is the zone axis and this is the hydroxyapatite. From mullite, this is the zone axis, and from alpha tricalcium phosphate, this is the zone axis. Now, these spots essentially tells you, this kind of spotty pattern essentially tells you all these phases are crystalline in nature. If there is a ring pattern in the transmission electron microscopy, then that will essentially indicate that is amorphous in nature, lack of crystallinity. Now this is the dark field image and this is the bright field image. So this set of bright field and dark field image essentially tells you that there is a partial weighting of this C2AS phase. This is the C2AS phase that is formed due to the reaction. This is your mullite particle, this is your Hap particle. Now essentially what it shows you that this is the partial weighting of this grain boundary by the C2AS phase, and this C2AS phase, if you take a selected area diffraction pattern, then this is 001 zone axis, and along that you can find that there are spot patterns, and then this is the spot patterns, then again this C2AS phase is crystalline in nature, not an amorphous phase. Okay. Other things that you can notice, this is a EDAX spectra that you can get in the TM from the C2AS phase. If you take, it shows the calcium peak, strong peak, because it is 2 CaO. So that means the calcium peak should be strong. You have also reasonably aluminum peak because it's Al2O3 is also there, and also you have SiO2. So that silicon peak also comes from that. So essentially the combination of SADP pattern, that is selected area diffraction pattern, coupled with this EDS analysis confirms the presence of C2AS phase as a grain boundary region in this microstructure. Now this is more bright field image, essentially tells you that there is a galenite phase here, which is a C2AS phase. You have these needles are essentially mullite needles, okay, and these needles are mullite needles which has a very high large aspect ratio of 8 to 10, and if you look at this is 200 nanometer. So essentially this width of this mullite needles is 200 nanometer, and also you have the CaO phase. And how to confirm the CaO phase? If you look at the EDAX pattern, it only shows you calcium and oxygen. So that means there is no doubt, undoubtedly it is CaO phase. Other things also, it is confirmed that it takes that in SRDP, that is selected area diffraction pattern, and at 001 zone axis you can see again these spots reflection planes. It essentially tells you that this is actually the coming from CaO. Now I have shown you enough of microscopy. Now let us discuss that mechanical properties or physical properties of these materials. Now as I shown you at the beginning of this lecture that hydroxide is essentially brittle phase. This has been proven again, this has been proved again. Now if you take the 5 kg load Vickers indent, then you can see there is a lot of this spalling or indent induced damage in this material. But when you make these composites, even at the 10 kg load, you can see there is a sharp Vickers indent. That means it is essentially damage resistant. If you look at that, so what I am trying to say here, if you take the 10 kg load in the hydroxyapatite, it will be even much more severe damage of the indent induced damage. But even at the 10 kg level in the composite, you can see the perfectly sharp and very well distinct Vickers image. Essentially tells you that this material must have better damage resistance property. Clear? The second thing that you notice that there is also some cracks which are forming, which is not that clear, but I can see on the image very closely that that there are certain cracks which are propagating from this Vickers indent corners, and based on this crack length essentially you can measure the fracture toughness. I will show you later. Now elastic modulus can be measured from two ways. One is the load penetration and one is the impulse excitation. Load penetration means like you take a micro indent, this is the loading curve, and your unloading curve will be like this. Now from the slope of this initial phase of this unloading curve, from this slope it will give you the elastic modulus. Now this is the load and this is your penetration depth, that is H. So from that you can find out that what is the elastic modulus of these materials. Another way you can measure this elastic modulus is impulse excitation. Like you take a bar samples, you can impulse it with some hitting with some steel balls or something, or tungsten carbide balls, and then you can measure the resonance frequency. You apply certain general formula, you can get the elastic modulus of these materials. Now independent of what measurement technique you use, the message from this slide is that you can get this range of these elastic modulus which is roughly around 45 to 85, and this 45 to 85 gigapascal elastic modulus which will closely correlate with that elastic modulus values of the cortical bone, that is the natural bone. So therefore, this hydroxyapatite mullite materials, that depending on the sintering temperature, that you can find out that what is the elastic modulus values which you require for real applications. Let's look at the strength properties. Now the strength properties for ceramic materials, you can measure only the compressive strength. Compressive means you can take a sample, you can put a pressure from both the ends, then you can measure that what is the load at which sample is broken. From that you can calculate what is the compressive strength. And we have also measured the 3-point flexural strength. 3-point flexural strength means you can take a bar shaped sample, you can put it, you can place this bar shaped sample on 2 support rolls. From the top roll which is placed at the half of the span length here, you pressurize it, you break the bar, you measure that what is the load at which the bar is broken, and based on this geometry of the sample and the load at which the load at the fracture point, then you can calculate that what is the flexural strength of this material. Now what you can notice here, that with increasing mullite content like half 10m, half 20m and half 30m, that means essentially means 10 weight percent mullite, 20 weight percent mullite and 30 weight percent mullite, your compressive strength is subsequently increases, and this increased value of compressive strength can go as close as 400 megapascal. Now 400 megapascal compressive strength in ceramics is quite a respectable number. Now if you look at the flexural strength, because hydroxyapatite itself is very poor in flexural strength, you can get a maximum of 80 megapascal. So you are getting close to 400 megapascal compressive strength, and you get close to 80 megapascal flexural strength in this material. And this combination of strength properties are quite good as far as the application of these materials is concerned. Now fracture toughness. Fracture toughness essentially means what is the resistance to the crack growth in these materials. Okay, so the property which describes the resistance to crack growth, that is what fracture toughness means. Now we have measured this single edge V-notch beam technique. Now single edge V-notch beam technique means you make this V-notch here at this root of this one, and then you can put these V-notch beam samples in the tensile side, and then you put it under these 2 support roll here, and from this 2 top roll you can apply this P by 2 load. Okay, then you can find out that at what load from the equilibrium of this point, these 2 support rolls also must support the P by 2 load at each point. Now this is called 4-point flexural configuration. Now based on this different crack length as well as the fracture load and so on, you can actually calculate that what is the mode 1 fracture toughness. K1C stands for critical stress intensity factor under mode 1 loading. K1C, often the students pronounce it KIC, which is wrong. K1C stands for critical stress intensity factor under mode 1 loading. Now the other way you can measure the fracture toughness for brittle materials like ceramics is that by crack length measurement, and this crack length measurement, it has been shown, for example, if this is a 2C, that is the total crack length, in both longitude and transverse direction you can measure this 2C crack length, and then based on this diagonal 2A, then you can adopt different formula, like formula proposed by Kochi Nihara tells you that K1C is nothing but 0.018 multiplied by H. H is the hardness, A is the half diagonal Vickers diagonal, E is the elastic modulus, H is the hardness, C is the half of the crack length. Now if we apply this formula, you can get a value of the fracture toughness of these materials. Now we have measured these 2 properties, fracture toughness, using both the values, like both the indentation toughness as well as the ACVNB value. What you get here in the ACVNB value, the fracture toughness value does not overestimate, but in the indentation toughness, fracture toughness values overestimate. And what you get here, fracture toughness is 1.5 MP square root meter, that is the ACVNB value, single edge V-notch beam value, and that is the value you can get it both 20% mullite and 30% mullite. In pure HAP, your fracture toughness value close to 0.6 MPa square root meter. So, this is 0.6 and this is 1.5. Now, if you look at this value, if you compare the what is the toughness of the base material, that is hydroxyapatite, you can immediately realize that there has been modest improvement in the fracture toughness values. The other thing that I must mention here, that if you go to the ACVNB value, this value is most reliable, and many times in the community, ceramics community, people have questioned the measurement of this fracture toughness using the indentation technique. So, this is a question mark. So, therefore, whatever value you are getting from indentation, that is also question mark. However, this value, that what you get in the single edge V-notch beam technique, that is the most reliable, because it does not overestimate the toughness properties of this material. Let us see some table which essentially tells you that what is the typical toughness values of the different materials which are developed, why they are different research groups. Now, if you take the hydroxyapatite based materials, it is a 0.6. In the 20 volume percent white ZP half composite, it is 1.5. 20 volume percent alumina half composite, it is 1.25. In the glass ceramic, it is 2 MPa square root meter. Now, unfortunately, all these materials, all these toughness values are obtained by the indentation toughness only, or indentation cracking only. So, essentially, again I can put a question mark here, because if you measure the ACVNB toughness values of these materials, I can very well tell you that these values will further decrease. So, whatever you are getting 1.5, it will not be 1.5, but it may be below 1 even MPa square root meter. So, what I am trying to say essentially that the toughness values that which are being measured with the hydroxyapatite mullite values certainly tells you that you can get a good ACVNB toughness properties from these materials, which are not being even achieved with any other materials which are reported till date. Now, in vitro properties, this is a kind of standard protocol for this in vitro properties. First, you have to do the steam autoclave, and either you can do autoclave by steam autoclave, or you can do autoclaving by gamma radiation. Now, for the ceramics like hydroxyapatite based, so on, that steam autoclave is okay. Then you have to seed the cells on these materials. You can take the 96 well plate, or you can take that 6 well plate, and so on. So, this is the micro well plate, and then you can put these materials inside the CO2 incubator, where there is atmosphere is maintained at 5% CO2, 95% air, and then also you have the good amount of humidity that is maintained inside the CO2 incubator. Now, you can do the cell adhesion test, then you can do the dehydration or the serial dilution, then you can further use the critical point triad, and you can proceed towards the ACM or fluorescence microscopy to see the morphology of the cells. Now, alternatively, you can use some biochemical assays. So, these biochemical assays essentially will quantify certain cellular fate processes. What are the cellular fate processes? MTT, that will give you the cellular viability. Then ALP, that alkaline phosphate, that will tells you the osteoblast differentiation capability, and osteocalcin tells you the bone mineralization capability. Now, L929 is the mouse fibroblast cells, which is the connective tissue cells of the connective tissue of the mouse. So, these are cultured for 24 hours on different hydroxyapatite, 20% mullite, 30% mullite, and this is your control sample. Now, if you compare this cell adhesion as well as cell proliferation with this one as well as with this one, you do not see much difference in terms of the cell adhesion and proliferation. Interesting features that you can clearly see here, that is cell to cell cellular network, okay, and this cellular network you can see very clearly here, and this is somewhere it's called cellular bridges, cell bridges. And overall, all the hydroxyapatite mullite surfaces are completely covered by these L929 cells, and this shows good biocompatibility, in vitro cytocompatibility property of these materials. Now, MTT assay was performed trying to quantify that cell viability of these materials, and as far as the cell viability is concerned, you can see that this is for the pure hydroxyapatite, this is for the hydroxyapatite 20 mullite, this is for the 30 mullite. Now, you see here this error bars overlap, and from these to this again it's roughly the error bars overlap, and these error bars overlap. So, what I am trying to say here, that for this, as far as the MTT assay is concerned, this hydroxyapatite mullite, they have similar MTT values like the pure hydroxyapatite. And what it means? That means when you add 10 to 30% of the mullite to hydroxyapatite, you do not compromise anything as far as the cell viability is concerned. That means you are not reducing the cellular viability by adding this mullite to hydroxyapatite samples. Now, as far as the ALP expression is concerned, that alkaline phosphatase activity, and these tests were done for 3 days as well as 7 days, and this is the statistical analysis performed for p less than 0.05. And what you see here, that for the 3 days, this pure hydroxyapatite and 10 to 20 30 mullite does not show any statistically significant difference except this one. But here in the 7 days, the difference is quite significant. If you see, compared to this hydroxyapatite to all these materials in 10, 20, 30, that significant difference is obtained. That means that these materials, they show better osteogenic differentiation property in this when L2 L929 cells were cultured on this material. These are like Mg63, that is the osteoblast like cells were cultured on this material. Now, osteocalcin, which is a bone mineralization. So, essentially this bone mineralization, so bone mineralization property are evaluated. Then again for this pure hydroxyapatite and hydroxide 10% mullite, this 20 and 30 they really stand out. That means this 20 and 30% mullite materials, they have better ability for the bone mineralization, and therefore they have better osteocalcin expression when Mg63, that is osteoblast like cells, were cultured on these material surfaces. Now, what was the reason for this difference in this in vitro cytocompatibility or in vitro that biomineralization property, etc. Now, first of all, you have to look at these AFM images of these materials. Now, atomic force microscopy images tells you that in the grain boundary region you have a microscale roughness. That means these grain boundary phases which are formed, that is C2AS phase, that is 2 calcium oxide, 1 alumina, 1 silica. This C2AS phase essentially forms, and that increases the microscale roughness of these materials. The second thing is that these materials actually they are like BCP phase. BCP means that is like biphasic calcium phosphate microstructure, and they contain beta TCP as well as the hydroxyapatite phase. And then other things, that BCP, that is biphasic calcium phosphate phase, has better osteogenicity than single phase hydroxyapatite. So that is also important, because if the BCP phase is preferred than hydroxyapatite, then as per the biological compatibility property is concerned, people always desire this BCP phase in the microstructure. Third one is this, as you remember the TM image, the transmission electron microscopy image, that these materials they have a calcium oxide, and the additional presence of calcium oxide also influences the biocompatibility property. Now, pressureless sintering of this hydroxyapatite, they always leads to multiple phases, and these phases actually also influence the mechanical properties to some extent. Now, next set of experiments that I will show, the results of these experiments that I will show, that to demonstrate that how these sintering reactions can be avoided in this hydroxyapatite based system. Now, for that we have carried out spark plasma sintering experiments, and this spark plasma sintering, as I explained to earlier, so it is like a hot press, but the fundamental difference is that large amount of current is made to flow from the anode to cathode during the spark plasma sintering, and this current is around 1 to 1.5 kiloampere, which is larger than that of the welding current that typically used in industries. Now, this current will flow either to the graphite dye-wall or to the powder compact, depending on the conductivity of the powder compact, porous powder compact, and this current will influence this high temperature generates around this neck region or the triple pocket region. And also because this contact resistance at the particle contact, they offer some kind of resistance to the current flow, that also increases the total heat generation at this neck region. And higher the temperature, more is the diffusion coefficient, and therefore more will be the diffusion and mass transport process which is required for this sintering to take place. Now, we have done experiments till from 1000 to 1050 to 1200 degrees Celsius, And what you see at around 1100 degrees Celsius, these materials we can get roughly around 100% theoretical density. Now this is that hydroxyapatite as synthesized, and then when you sinter this SPS this at 1000 or 1150 degrees Celsius, what you see, we do not see any presence of the hydroxyapatite tricalcium phosphate except at the 1150 degrees Celsius samples, and there is no other reaction product like calcium aluminosilicate or alumina or silica. Those kind of reaction product is not there. So it is very clear that if you use a spark plasma sintering, you can avoid those sintering reactions and you can retain both hydroxyapatite and mullite phase in the microstructure. So I think I'll stop here, and then in the next lecture I'll start with this hydroxyapatite based biocomposites, how to design this hydroxyapatite based biocomposite with significant bactericidal property.